Breadth First Search (BFS) is a fundamental graph and tree traversal algorithm that explores nodes level by level, making it one of the most widely used techniques in computer science for searching, pathfinding, and solving problems that require a systematic exploration of structure. Unlike depth-first search, which dives deep into one branch before backtracking, BFS works by visiting all nodes at the current depth before moving on to the next level. This level-wise exploration gives BFS unique properties, particularly its ability to find the shortest path in an unweighted graph, making it indispensable in networking, routing, artificial intelligence, operating systems, and many other computational fields. BFS begins by selecting a starting node, often referred to as the source or root, and placing it into a queue, which plays a critical role in maintaining the order of exploration. A queue ensures a first-in first-out (FIFO) process, allowing the algorithm to explore neighbors of nodes in the order they are discovered. After enqueuing the starting node, BFS repeatedly performs a simple cycle. It dequeues the front element, processes it, and then enqueues all unvisited adjacent nodes. By marking nodes as visited immediately when they are enqueued, BFS ensures that no node is processed more than once and that cycles in graphs do not cause infinite loops. Because BFS visits nodes in increasing distance from the source, it guarantees the shortest path, in terms of number of edges, between the source and every other reachable node, a property that forms the basis for many algorithms in communication networks, such as computing the minimum number of hops between two devices or routing data efficiently across a network topology. BFS is also crucial in applications where exploring a structure layer by layer is important, such as finding all nodes that are k edges away from a given node, determining connectivity between components, or exploring friend networks in social platforms where degrees of separation matter. In trees, BFS is commonly referred to as level-ordered traversal and is used to print nodes level by level, construct heaps, compute tree height, and serialize binary trees for storage or transmission. In graphs, BFS is used for bipartite checking, detecting connected components, computing shortest paths in unweighted scenarios, and solving problems like the minimum knight moves on a chessboard or the shortest transformation sequence in word ladder problems. Another important aspect of BFS is its space complexity, which can be significant because the queue may hold an entire level of the graph at once, especially in wide or dense graphs. This contrasts with DFS, which typically uses less space but cannot guarantee shortest paths. Despite this, BFS remains the preferred choice in many practical applications due to its systematic exploration pattern and its optimality in unweighted scenarios. BFS can also be extended through variations such as multi-source BFS, where multiple nodes are enqueued at the beginning, allowing the algorithm to compute shortest distances from several origins at once. This technique is used in problems like finding the minimum distance to a set of target nodes or spreading effects across networks simultaneously. Another powerful extension is 0-to-1 BFS, which uses a deck instead of a queue and is optimized for graphs where edge weights are only 0 or 1. Enabling efficient shortest path computation without using Dijkstra's algorithm. BFS also plays a significant role in artificial intelligence and game development, especially in search-based problem solving. For instance, BFS is used to compute the shortest number of moves in sliding puzzles, maze solving, and state space exploration where each node represents a state and edges represent transitions. Because BFS explores all states reachable within a given depth before moving deeper, It ensures optimal solutions when all actions have equal cost in database systems and file structures. BFS is used to scan B-trees, directory hierarchies, and indexes where level-wise processing is essential. Operating systems use BFS like logic in scheduling tasks, scanning process trees, and analyzing communication paths. In robotics, BFS helps robots map environments, determine shortest routes in grid-based maps, and navigate obstacles efficiently in unweighted or uniformly weighted contexts. BFS is also essential in determining the diameter of unweighted trees through a two-phase BFS, where the farthest node from an arbitrary starting point is used as a new source, and the farthest distance from that node determines the tree's diameter. In addition to these algorithmic applications, BFS contributes significantly to theoretical computer science, particularly in graph theory, where it helps construct spanning trees, classify edges, detect tree layers, and analyze graph properties such as distance, eccentricity, and girth. BFS can be implemented in both iterative and optimized forms, but its core principles remain the same. Use a queue, explore neighbors level by level, mark visited nodes, and ensure systematic traversal in increasing distance order. Its time complexity is O, V plus E, where V is the number of vertices and E the number of edges, making it highly efficient for both sparse and dense graphs. However, BFS may require large memory for wide graphs, illustrating the trade-off between time and space. Despite this, BFS remains one of the most trusted and universally applicable algorithms because its clarity, determinism, and predictability make it easy to implement and adapt. It stands as a fundamental building block for more advanced algorithms in pathfinding, clustering, graph coloring, and network flow problems. In summary, BFS is a versatile, powerful, and intuitive traversal algorithm that explores nodes level by level using a queue, guarantees shortest paths in unweighted graphs, and underpins a vast array of applications across computer science. Its ability to traverse systematically, discover layers, analyze connections, and provide optimal solutions makes it a cornerstone technique in data structures, algorithms, artificial intelligence, networking, databases, operating systems, and beyond.